Hello, I'm David. I'm the coordinator of the Maths Learning Centre. This is a Maths for IT revision seminar. It's semester 2, 2016. Hello from the past. That was for the benefit of those watching online. Hello to all of you from the present. This one's going to be about graphs, or graphs if you prefer, but I'm from New South Wales, so I pronounce it graph. Though I did know someone once who pronounced the word differently depending on whether it was a noun or a verb. So you would graph a graph. So, and plant a plant. Right. You can tell it's late in SWAT week because I'm becoming less and less coherent as the week goes on. Okay. So, taking a quick look through the lecture notes that I've borrowed from a very helpful student, thank you, for this. It's very mathematical in the sense that it's full of familiar words with brand new meanings, which is how a lot of pure mathematics goes. So, as far as I can tell, the main thrust of the section on graphs is knowing what all of those new words mean, basically. So, there are a couple of algorithms and there may possibly be proofs and things connected with them. But what I'm going to do first is have a search through here for all the terminology and write it all down. That's exactly what I would do if I was studying anything that had a lot of terminology. I'm just going to put it together. And then the useful thing about that is that future generations doing this course, if it still has graphs in the future, will have a handy little handout that has those things in it. And it will also be useful if I know what the definitions of everything is to solve any problems that might come up, say, from a past exam. Because as far as I can tell, anyone over the last few weeks who has asked me about graphs who has visited to the Maths Learning Centre, the main issue has been knowing what the words mean. So that's what I'm going to start with first. Let's start. All right, terminology. So let's see. We've got a graph which has a definition, but it's probably not necessary to do the full maths definition, but I'm going to put it down anyway. So our definition is that it's a pair where V is a set of vertices and E is a set of edges, and E is a subset of V cross V. Rightio. And that's your standard graph. Being a subset of V cross V means that it's an edge is technically, in the terms of the mathematician's definition, an edge is basically a list of the beginning and the end of that edge. So our meaning, so we have vertices we imagine as points. An edge is a pair of points, so something like A, B, where A is the beginning of the edge and B is the end of the edge. But what we do is we imagine them as lines. Line or arrow. Rightio. That's what it means. And so whenever you have a definition of something, You want to have things that look like that so that you can tell what is and what isn't. So it looks like we could have something like this. That would be a graph, but graphs will often have, in the traditional version, the graphs are all arrows. Everything goes from everywhere else. It is possible to have so here's one. It's possible to have things that connect to themselves. It's possible to have an arrow going one way and an arrow going the other way. It's possible to have a dot that doesn't have any arrows attached to it at all. They are all perfectly reasonable graphs. And I have a feeling that there is such a graph as the graph with no points at all, just to be consistent. So I have a feeling that that is such a thing that exists, or doesn't, I suppose, philosophically. So that's a graph. I think I'm not going to do this in the order that it is in the notes, because we have various other definitions of graph-like things. So I'm just going to move forwards a little and find something that I saw when I was looking through the notes yesterday. It may be that there are, I'm just looking for it. Oh, maybe they don't talk about this. That might have just been last year's notes. Sorry, guys, I think that this is why I needed this year's notes. Last year's notes had a few other different types of graphs. They had multigraphs and things like that, but I don't think multigraphs appear in this year's course, do they? They do, and I'm just not seeing them. Is there more to this than what I have here? Sorry?
It sort of just flew past that.
Right, it just was mentioned in passing. Oh, there it is. I'm going to put it down. I found it. The only reason that I can see that multigraphs appear in your course is so that they can use the bridges of Königsberg as their motivating example. Whatever. So a multigraph is like a graph, except that there's allowed to be more than one edge going from one point to another. So one of the things about this definition is that when we talk about a set being inside V cross V, that means that the path can only be there, like not path, but that edge, that arrow is only there once. So if point 1 and point 2 are connected by an arrow in that direction, then there's only one arrow going there. So, that's an assumption here that's sort of not stated, but it is implicitly part of it. So only one, well, at most one edge goes from one place to another. From one vertex to another. But if you're allowed to have more than one, well, that's called a multigraph. So you're allowed to have more than one. That's how that's the meaning. The definition is that it's actually a set G is a pair of vertices and edges. V is the vertices and E is the edges, and E is a subset now of V cross V and the numbers, the natural numbers. And so you can have, so e.g. you can have point A, B, edge number 1, and A to B, edge number 2, etc. Conceivably, at the moment, it's not at all necessary to start at 1, but that seems reasonable. The numbers don't have meanings other than to label the edges. So these are 2 edges. From A to B. As far as I can tell, the only reason multigraphs are in here is so that we can talk about the bridges of Königsberg. Great. Which is an example like this, which has multiple paths from A between here and here. Okay. Now, there is technically one more kind of graph, which is a weighted graph, which technically is not a graph, sort of a type of graph in its own right, but in a way it feels different, so I'm going to put it here. So you've got a weighted graph, and so the meaning is it's like a graph. So it's like a graph, but each edge has a number attached to it. Called the weight. And so what really technically it is like the definition is that you have a graph G VE with a function weight which sends the edges to the real numbers. Basically what that means is that every edge, there's a formula or a table somewhere which tells you what number is attached to that. Calculate the weight of edge E as WE. That's what it is. The reason I'm putting all of these here is because they go with certain pictures. I really should have drawn a picture of my multigraph, I'm sorry. So go back and fit one in here. Something like that would be a multigraph, because we have more than one edge going in the same direction between various points, various vertices. So that's a multigraph. And a weighted graph, it could be any kind of graph, but there'll just be numbers attached to the edges. So maybe this one will be 1, this one will be 0.3, this one will be 4, this one will be 8, this one will be 5.7, something like that. You'll usually see them with whole numbers on them, but there's nothing stopping them from being any number you like. Alright, the reason I put them all together is that in my head they go with the picture of what the graph looks like. And so when I see the picture, I can go, oh, it's got numbers attached to it. That's a weighted graph. Oh, it's got more than one arrow going from one place to another. That's a multigraph. I do have one more. Yep?
Does that mean you could combine weighted
Yes, you could have a weighted multigraph. Yep, totally thing that you could do. Most of the terminologies that go with this course go with ordinary graphs rather than multigraphs. You would have to define trees different. Anyway, there would be all these things that you would need to define. But you could have weighted multigraphs as well. Right, so there is one more picture that you will see which doesn't correspond to a whole type of graph of its own, and sort of corresponds to two more new terminologies. So, unfortunately, we need to have the definitions of those terminologies first, but since we're studying it from this end, having seen all the terminologies, I'm going to mention it now. So there are loop-free graphs, where loop needs a terminology of its own, and I will write that down shortly. But there are loop-free graphs, which are ones where there are no loops, and a loop is an edge that connects a vertex to itself, I think. I'm going to trust that that's true, even though I can't find it. So this is loop-free. Not that one. That's loop-free, even though it's technically possible to go all the way around and get from this point back to itself, but there's no way of doing it in one step. So this has got no loops, and this one's not loop-free. Because it's got a loop in it. Only has to have one loop in it to not be loop-free. And so this thing here, this is a loop. Okay, and I will write down definition of loop shortly, but Okay, so a loop-free graph has no loops. Okay, and then we would have what they call undirected graphs. I'm not going to put directed, I'm just going to put undirected graph. So in a way, an undirected graph is a type of graph all of its own. And what it looks like is there's no arrowheads. This one is directed because it matters which direction you go from one to another, and it's possible to have ones that go one way or the other. That's a directed graph, whereas an undirected graph has no arrowheads on its arrows. On its edges. Something like that. There is a specific definition. Their definition is quite interesting, actually. When the definition mathematically of an undirected graph is almost as if it's a doubly directed graph. All the edges go in both directions. And that's the definition of an undirected graph based on the original definition of graph. So you can say the definition is that G, which is made of a set of vertices and inverted edges, is undirected when A, B being in the set of edges happens if and only if BA is also in the set of edges. i.e., that is, all of the edges go in both directions, which means we don't need arrowheads on them because you can go down them either way. So your earlier question of your sort of multi-weightedness, sort of a weighted directed graph, even if the arrowheads go in both directions, if they have different weights, it doesn't count as being an undirected graph because maybe forwards has a higher weight than backwards. So if there are weights, technically it only counts as undirected if the weights are the same in both directions as well. So our definitions are colliding in unexpected ways, which we haven't actually talked about in the course. So I wouldn't imagine it would come up. Yes. All right, that's a definition. So i.e. all arrows go both ways. But the way we draw it is to just not put any arrows at all. One of those things. And so one of the things about the way mathematicians come up with definitions for things is that they don't always match exactly with your intuition of how the picture works. And the reason they've chosen them the way they are is because it's the easiest way to do proofs. And it's also often the easiest way to encode them inside a computer. The easiest way to encode a graph inside a computer is as a matrix, which I'll get to shortly. When you think of it that way, then the matrix lists things in both directions. And so you think about it a little bit differently when you're thinking about it inside the computer. And so that's one of the reasons the definition is chosen the way they are, is because of computer programming. Which is interesting because they were invented before computers, but that's just... But computer science grew out of maths because that's how a lot of mathematicians thought about things, and so it all makes sense in the end. Okay, so there are types of graphs. So far we have ordinary graphs, multigraphs and weighted graphs, loop-free graphs and undirected graphs. There was a note in your course is that when people say graph without qualifying it, they usually mean an undirected loop-free graph. So, unless specified otherwise, people mean loop-free undirected graph when they say graph. And just be careful, they might not explicitly say that they don't mean loop-free undirected graph, but it will be there because of context. And they'll say something like, you know, consider the graph G equals VE, prove that if this happens in one direction, then it happens in the other as well, and then you know that it talks about directions, so it must be a directed graph. So, and look at the picture carefully because it might have arrows on it, which means it's a directed graph. So just be careful that it might be the context that tells you that it's not a loop-free undirected graph, but if nothing tells you that it's a loop-free undirected graph, that it's not that, then that's what they mean, even if they don't say it explicitly. Yes. I mean this otherwise stated is sometimes a little less clear than you would like, but most maths lecturers here at Uni of Adelaide are quite precise and will definitely tell you otherwise. Okay, there is one more other type of graph. It will of course require us to define a specific type of information about a graph. But I'm going to put it here anyway. A tree. So the definition A tree is a connected graph with no cycles. Now that requires us to define what we mean by connected and what we mean by cycles, but I'm putting it here because it goes with a picture. So sometimes, even if you don't know what all the words mean, a useful way of thinking about it is to think of pictures of things that are and things that aren't. That's how most definitions are encoded in a human brain, as a big list of things that are and a big list of things that aren't. And so it's a useful way of understanding maths things, but as long as you get the definition eventually. So here are some examples of trees. This is a tree. This is not a tree. Because in the naive understanding of what connected means, it's not connected, but that is the real meaning of what connected means as well. So this isn't a tree because the pieces aren't connected to each other. If this was connected to here, it would be a tree. See if I can find some good ones. This is a tree. And I'll go back with the definition. But it's connected. And a cycle means that there's a way of going round and coming back to where you started, which there is not currently at the moment, a way of doing that. This is a tree. Doesn't actually have to have any branches to be a tree. And I suppose I should put one in with that doesn't have, that has a cycle. That's not a tree. And just because we traditionally write them from the top down doesn't mean that they're not trees either. I mean, that's one of the reasons I included this one. This looks like a tree. I mean, it's upside down, but it looks like a tree. We don't have to draw them up that way. There's nothing stopping us drawing a tree in whatever way we like. Okay, it doesn't have to be up anyway. It looks vaguely cat-like. That one. So these, as far as I can tell, are all of the types of graphs that appear in this part of the course. Yep. Ah, well, what's a forest? It comes after tree, I suppose. Oh no, there's more, there's bipartite graphs too. Damn it. Well, where is forest? It must be after tree. Ah, a forest is a graph whose connected components are trees. Okay, so a forest is a graph that's made up of separate trees. So the definition is a graph whose connected components are trees. We've got a thing here. We need a definition of connected component in order to know what a forest is, but we can do some pictures of it. So basically, so the meaning is basically a collection of separate trees. That's what it is. So an example would be, put some vertices in. That there is a forest, because each piece is a tree. That piece is a tree, that piece is a tree. So we can go like tree. And it could have as many of those as you like, I suppose. That would be a forest as well. Because what it is, it's made up of 3 trees. Like that. That's what a forest is. So anything that's not a forest is basically anything that's not a tree, that has a non-tree anywhere inside it.
So is a single tree a forest?
A single tree is indeed a forest. Let's pop that in. A forest with 1 tree. Mathematical definitions in general do not require you to have a particular number of things in order for them to exist. And so when the name sort of implies that there's more than one, most mathematicians will go, no, just having one is enough. Sometimes not having any will be enough. So in Maths 1A you talk about convex sets, and the empty set, which doesn't have any points at all, is a convex set. So you don't necessarily have to actually have more than 1 tree for it to be a forest. It's just a very small forest. Yes, so it's a worthwhile thing to note about the way maths definitions work. Even though the definition says connected components, it's allowed to refer to just one object. Okay. And then there's a bipartite graph, just while we're at it. Wow, it turns out that there are a lot more different types of graphs in this part of the course than I thought. So bipartite graph. It has to be undirected, though I don't see why it has to be, but according to your notes, a bipartite graph is an undirected graph. Definition. An undirected graph such that where the vertices is made of 2 subsets, for U and V. This is the maths definition. I'll interpret it in a second. And any edge AB has A in U and B in V, or the other way around. Okay. So this is the math definition. It's referring to the set of vertices. It's referring to the set of edges. So what this is saying is that... Sorry? Yes. Good thing that's easy to fix. What this is saying is that there's two blobs of vertices that are separate from each other. So it's saying if we collect all the vertices together, we can make it out of two pieces. The two pieces are not equal to, actually is equal to the phi. Sorry about that. The vertex is made of two pieces, so the pieces join together. That's what the union symbol is for. U union W is V. These two pieces join together to make V, but when you overlap them, there's nothing in the overlap. So the intersection of these two sets, U intersection V, is empty, so there's nothing that's in both of them. So you can collect together one group of vertices and another group of vertices. Together, that's all the vertices, and every edge goes from one group to the other group. That's what it says. So let's make some. Let's see if we can do it. This is the hard bit. Do you reckon we can make that into a bipartite graph? So one way I'm going to do it is I'm going to... So this vertex here, these two can't be in the same part. The bipartite graph has two parts. That's what the bi means. So these two have to be in the other part because they're connected to this one. So basically it's saying that if they're in the same part, they're not allowed to be connected to each other. Okay, so this one's connected to that one, so that's in the other part. This one's connected to that one, so that's in the other part. All right? These two have to be connected. This is connected to that, so this must be in the opposite part to the blue bit. This is connected to that, that's in the opposite part. Damn, these two are connected and they're in the same part. So this is not a bipartite graph. But this one, oh, do those blue and red look the same to you? Marginally, they are not at all different. Sorry about that. I will just distinguish them in some other way. Okay, so what I did is I started here and then coloured things in if they had to be in one part or the other. So if we removed this edge here, it would have been a bipartite graph. So let's start again. That blue one. These other two that are connected to it have to be in the opposite part. They're going to be squares. So anything that's connected to a red one can't be red, so it has to be the other colour. Anything connected to a blue one can't be blue. Nope, that's not the one I wanted to remove. I want to remove that one. So if I remove that edge, it's not there anymore. Then we end up with and nothing red is connected to anything red. The square ones, the red square ones, aren't connected to each other, and the blue circle ones aren't connected to each other, And so that becomes a bipartite graph. In fact, this one's just a big loop, a big path, interestingly. So this one is bipartite. I started here. But the traditional way of drawing them is more like this. Like that. And this one again has the same property. If I colour this one, I'm going to do it as a circle, then these two are connected to it, so they must be in the other half if there is two halves. If I colour this one in, this one has to be in the other half. In fact, what's going to happen is that all these ones are red and all these ones are blue. So I've got two completely different pieces and nothing that's in the same piece is connected. And any edge that actually exists goes from one side to the other. But there's nothing stopping you actually drawing them mingled in with each other. It's just easier to imagine it when they're not. And so what we have is that we have that this one over here, I might even do it in blue. That might be my U, and this bit here would be my W. And all my edges go from U to W. I have to say, I have never understood bipartite graphs until just then. It makes more sense now. And I've never been able to know how to tell if a graph is bipartite, but now we have a nice strategy. Start by marking one of them, and anything it's connected to must be in the other half, and anything that they're connected to must be in the first half. And at any moment where you have two things connected that are the same colour, it's not bipartite. Awesome. I can also see an awesome exam question if I was the lecturer for this course. And so show that a tree is bipartite. I reckon all trees have to be bipartite graphs. Pretty sure. Could be wrong, but I'm pretty sure. Because if we go back to our trees, this tree here, for example, if that one's blue, this one will be red, which will make all those blue, which will make these ones red, and none of the ones that are the same colour are connected to each other. It's awesome! That would be a great exam question. I might even try and do an example of it in a minute. Okay. Why do we care about bipartite graphs? It's so that we can give you some standard graphs that you can make. So we've now, let's just see, where have we been? Wow, it's taken way longer than I thought, but I'm really pleased with myself for organising all of this. So we've got ordinary graphs, multigraphs, weighted graphs, loop-free undirected graphs, trees, forests, and bipartite graphs. Yep?
I think you forgot the subgraphs too.
Sorry? No, I reckon subgraphs would be fine. I'll get to that. If I mention anything that you like, that you want to know about, I won't, but subgraphs are smaller parts of existing graphs, so they don't exist as things in their own right. And at the moment, this list is things that have their own identities sitting by themselves. So that's my organisation in my head. So now we are up to one more thing before we leave off our terminology for particular kinds of graph. So I think that's all the... I'm going to call them free living. It's not a real word, but they live by themselves. They don't exist. Subgraphs don't exist separately from other graphs. They're always inside another graph. So these are all the free-living kinds of graphs that we need to do. We've now got some lovely ornithology, which I call it, bird watching. We can see a graph in the wild and go, "Oh, it's a bipartite graph. Put it in my sketch, put it in my notebook." And so that's what we've got. But what we need is there's a couple of them that aren't just in a particular category, they have a specific name. So that if someone says to you, "Oh, I've seen," you'll know exactly what it is. And so we have some specific named graphs. And they are Kn, which is the complete graph on n vertices, which means that it's an undirected graph, so technically it's undirected. And basically it has n vertices and every vertex is attached to every other vertex. So all the edges are there. So that's what it's called, and the definition is has n vertices and every possible edge is there.
So mathematically that would be is equal to v cross v this time.
Yep, basically. Well, sort of v cross v, yeah. i.e. E is actually equal to v cross v. Undirected graphs equal to v cross v is a bit weird, but it'll be okay. And so what you do is you can just do some examples. This would be K5, and this has to be connected to everything. This has to be connected to everything. This has to be connected to everything. This has to be connected to everything, and this one's already been connected to everything. That's K5. And K7 would be similar. You just, if you want to draw one, you'll just run through all of the possibilities. It doesn't necessarily have to look like that, but in general, the simplest way of drawing them is to draw them as a star. The notes here have K3 drawn wrong. I'm just going to correct it for you. Okay. So K3. This one has to be connected to both of the others. This one has to be connected to both of the others. And this one has to be connected to both of the others. K3 is just a triangle. You're missing an edge. I'll just fix it for you in your notes. Okay. And one of the reasons to be able to mention bipartite graphs is to have another graph that has a name. So I'm going to go straight to the next page. Oh, I should just say this is not K4 because there's an edge missing. Just so you know. There's a missing edge across this diagonal here. All right. So KNM is the sort of complete in inverted commas is a complete bipartite graph. With parts of size n and m. So what that means is that the definition is that U has n vertices, VW has m vertices, and every edge AB for A in U and B in W exists, basically. So I should have actually said G equals U union V E. And so to draw them, if I wanted to draw K1, well, maybe I'll do a bit bigger than that, 4, 3, there'd be 4 here and 3 here, and every edge from here to here exists. So this has to be joined to all of them. This has to be joined to all of them. This has to be joined to all of them. And this has to be joined to all of them. And now it's done. Every edge, every vertex on this side is connected to every vertex on that side. K1, 5. Would be this, which is a tree, by the way. And so on. Basically, that's the deal. But if any one of those edges is missing that connects one side to the other, it's not one of these things. It's not complete. So what this means is that these ones have names, which means that any moment someone could say, "Ah, could you tell me all about K43?" And you could go, "Oh no, I know what K43 is, it's this one." And then you can start counting edges and vertices and stuff like that. Okay. We have now done all of our bird watching for graphs, unless of course there are more. Oh, I should just point out that let's do K23 just want to finish something off. So that's connected to all 3 of those. That's connected to all 3 of those. Oh no, that is not what I was hoping for. Huh, that's okay. I've just got lots of different examples now. All good. Sweet. But they don't have to look like that in order to see them. Okay, so if you want to know whether something is K23, you know it has to have 5 vertices because that's how many it has to have. You'll have to turn it into find out whether it's a bipartite graph, and then you will have to see if everything on one side is connected to everything on the other, and then you'll know if it's the one that you were looking for. So it's not really productive to say, is this K23? It's much more productive to say, draw K23, and you can just make it yourself. But it's quite difficult to tell if this is one of the graphs you're looking for, because telling if something's bipartite is not straightforward, as we've just known. But we have found a nice way of doing it, so we've got it. Okay. Right. Now where are we up to? That's all of those things. And so now we're up to, we have all the types of graphs that we're interested in. We're now up to things that one could say about a graph or find within a graph. So here we go. Things to find inside graphs. What might we find inside a graph? We may find a loop. An edge connecting a vertex to itself directly. There's a loop. It doesn't have to be nearly so simple. Right, yeah, loop, loop. Okay, nothing stopping you from drawing it round the outside other than confusing the person who's reading it, but sometimes that's the point. That's a loop. Okay, what else have we got inside a graph? We can have paths. So what does it say about a path? A path, oh no, so before paths, walks. This is fun. But we have walks, and it says here, a walk is a sequence of vertices such that there's an edge between each pair of them. So this is the definition. A walk in the graph G sequence of vertices V1, V0 say, V1 up to Vk, such that every edge Vi plus 1 exists. Alright, is in the set of edges. Okay, so what does that look like? Well, it just looks like a way of going all the way around, right? So I have to name the vertices to do this. So you can see what it looks like. So I'll call this vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7. Really should have called them ABC. Too late now. So my walk just has to go from one place to another. Something like that. That would be a perfectly good walk. And so my walk is 1, 2, 5, 2, 7, 4, 3. That's my walk. There you go. It goes in a certain order, of course. So walks have arrows even if the original graph doesn't. So that's a walk, and a path. Actually, I'm not going to do path next. I'm going to do circuit next. So the circuit is a walk where the first vertex is the same as the last vertex. So here's something that's not a circuit. Again, the green is not easy to see, is it? It can just look like it's in bold. Okay. Not a circuit, because it doesn't end where it starts. In fact, I should just say up here something that's not a walk. You will realise that I'm going to give you these pictures afterwards. Okay, they will go on my website. So not a walk would be like that, for example. So if I had 1, 2, 7, so if I listed 1, 2, 7, 4, 3, it's not a walk because, no, that is totally a walk, isn't it? Put this 5. Right. It's not a walk because there's no path that goes from 3 to 5. So a walk only works if there's a path that goes from each step to the next step. So 3, I can't go direct from 3 to 5, so it's not a walk. It's worth pointing out. If I was lecturing this, I reckon I would give some pre-handed out graphs that you could draw on, rather than having to copy the graph itself in the lectures. Did your lecturer do anything like that? Didn't get you to draw things on graphs during the lecture? They did? That would have been fun. So a circuit this would be a circuit. Like that. It comes back to where it started. So if this was 1, 2, I could do it as 1, 2, 3, 2, 6, 5, 1. I better label these. 1, 5. Okay. But technically as well, if we had that problem, if we had in the middle here 2, 4, it wouldn't be a circuit because it wouldn't be a walk either. There'd be a gap in the pathway. So why do I care about those? Not sure at the moment, but we'll run with it. And then as a subclass of both of those, we had walks and circuits, and then there are also paths and cycles. Path, where no vertex is repeated. So So this isn't a path. I've actually traced the whole thing, but let's put an extra one in so that it doesn't look so bad. 1, 3, 4, 5, 2, 4. That's not a path because I've done 4 twice, but it is a walk. And whatever. But this is a path. I mean also a walk. Any path is a walk, that's the point. A path is a special kind of walk. And a circuit is a cycle. We already did circuit. No repeated vertex. Except the first and the last one. Which have to be the same for a circuit anyway. I decide not to draw that. I'm pretty sure it's clear right now how that goes. But I just want to put them together. We've sort of got a path. We've sort of got like a walk and a circuit. And we have a path and a cycle. And these two don't come back. Like circuits are special kind of walks, paths are special kind of walks, and cycles are special kind of both of these. Like that. So a cycle is a circuit that's a path, basically. So cycles are walks, paths, and circuits. Circuits are walks, but not cycles necessarily, but they might be. That's the idea behind it. And so these ones are, these ones over here have no repeats over this side. And down here, these ones come back to where they started. Well, I guess end is the beginning. That's a way of organising those terminologies. And all of these things are things that you can find inside another graph. We'll get to that. Let's see what a simple walk is. Right. So a simple walk is one where I better put that in just a second. A simple walk, no edge is there twice, but the vertices are allowed to be there twice. So I guess that means that one of the ones that I drew before was simple walk, but not a path. I had 1, 2, 3, 4, 5. So this walk here which went 1, 3, 4, 5, 2, 4 is a simple walk. But not a path. This one would be, if I just do the same graph again, this one would be a simple Give me a second. One, 5, 4, 2, 5, 4, 3. This edge is there twice. And so this is not simple. It's still a walk. A non-simple walk. And therefore, since it's not simple, it can't be a path. Because a path doesn't include edges, vertices twice, so it can't possibly include edges twice. Oh, here. So technically what we have is in here, we have simple in here. Like that. And technically there are simple circuits too. Man! So we could go this way to go simple that way too. I might as well. There you go. Tell anyone who wants to watch who wants to do this to watch that bit live, because that table's not going to make any sense. So what have we got so far? We've got all these different kinds of graphs. We've got things to look for inside graphs. Okay. What else can we look for inside graphs? We can look for subgraphs, spanning trees, and connected components. All right. Okay, just point out that now that we've seen what a circuit is, we almost know what a tree is, because we know a tree doesn't have any circuits. So note. Trees have no circuits. They have no cycles either, but that's not relevant. Oh, I guess they can have circuits, I suppose. They have no cycles. Every graph with an edge has a cycle, has a circuit, because you could go 1, 2, 1 and just go forward and back again. Damn it. Right, so trees have no cycles, because a cycle can't have, interestingly, 1, 2, 1, no, not allowed to have edges, repeated edges, or repeated. I'm just going to do that, no edge. It's not just repeated vertices, but no repeated vertices or edges, because in a very special cases, if you just had 1, 2, 1, that's not a path, even though the vertices aren't, that's not a cycle, even though the vertices aren't repeated. So, no repeated vertex or edge. No, it doesn't pass the simple test, which matches with this picture here, but I need to put it in the definition because otherwise it doesn't work. So you could say it's a simple circuit with no repeated vertices, if you like. That'll work too. But I'm just going to say or edge. I'll put an or edge there. I'm going on way long, I'm sorry, but just, I want to do this properly. Okay, this is exactly how I would go about any topic trying to understand it. It's walking through and figuring out how everything's connected to everything else. So trees have no cycles. Okay, we've done that. So other things we can find inside other things is connected components. But I should just say what the word connected means while I'm at it. No, I'll just do it. So the connected components would mean the parts of it that are connected to themselves. There's a definition here. Yeah. So, I'll just put the definition of connected in here. So connected means, the definition says that every pair of vertices is joined by a path. Basically. Yep, every pair of vertices is joined by a path. That's what connected means. And the connected components are the parts of it that are connected. So you take all the sets of vertices and go, all these ones are connected to each other, and all these ones are connected to each other, but together they're not connected. So sort of the biggest collections of connected vertices. So we can do this, we can go this one's connected. And this one's not connected. And what it has is this one's got two connected components. I know it's not connected because there's no path from here to here. There's no way of getting from this vertex to this vertex. That's impossible. So it's not connected. I'll just label them 1 and 2 if you like. Let's call them 1, 2, 3, 4, 5, 6. 1 is not, well, I can say no path from 1 to 3. There is no path from 1 to 3. That's why it's not connected. And what we have is two connected components. We have this bit and this bit. So to find the connected components, just start anywhere and find anything that's connected to that and anything that's connected to those and colour them all in the same colour. And then do it for everything else, and they are my connected components.
In a way, that's like complete opposite of the bipartite.
Exactly. In fact, it is possible to be both connected and bipartite. It's possible to be not connected and bipartite. It's possible to be neither connected nor bipartite. But it's a similar approach to how we would do bipartite. So with bipartite, you'd start with one of them and you'd colour anything it's connected to in the opposite colour and back and forth. But to find connected components, you'd colour everything that's connected to it the same colour. So you can have as many connected components as you like. Now just be aware that the word connected refers to the component itself individually. It's not saying the components are connected to each other. It's saying that each component is connected to itself. That's what it means. So it's an unfortunate terminology, but we're stuck with it now. So, for example, this one would be disconnected as well. I'm just going to say the components are 1, 6 and 4. And 2, 5 and 3, they are my connected components. So here if I label them 1, 2, 3, 7, 8, it's not connected. A little more obvious because the paths aren't the edges aren't overlapping, and we have components 1, 6, 7, 8, 2, 4, 5, and just 3 because it's not connected to anything else. They are my connected components. So, basically, you could define forest before tree. A forest is any graph with no cycles. And a tree is a connected graph with no cycles. So, just going to point that out now. Note, a tree is connected. That's the definition of a tree. It's a connected graph with no cycles. But a forest is just a graph with no cycles. But what it ends up happening is that each piece of it ends up being a connected piece with no cycles, so each piece has to be a tree. So a forest is a graph with no cycles, but might not be connected. So that's where we are there. So one of the reasons that, we've noticed certain things, trees sort of have some sort of tree-ish property to them that makes them easy to calculate things about, but we've also got a property that separates trees from other things, which is having cycles. And we have a property that separates trees from forests, which is we have a property that separates trees and forests from other graphs, which means they have no cycles, and we have a property that separates trees from forests, which is connectedness. And the other thing that a graph might own, if you're looking for things inside it, is that you might have trees inside it. Subtrees, if you like. Subgraphs. Did I talk about subgraphs? Yeah. Oh. All right. Technically, pretty much everything I've mentioned inside another graph is a subgraph. So these connected components, they're subgraphs. Cycles, subgraphs. Paths, subgraphs. Everything inside another graph that's made out of some collection of its vertices and edges is a subgraph. So this is a definition, given a graph G which is equal to a set of vertices and edges, a subgraph is for V1 contained in V and E1 contained in E. So the meaning, some collection of the vertices and edges. You could actually collect all of the vertices and edges, and then every graph is a subgraph of itself, but that's stupid, and that's why they have this thing called a proper subgraph, which is a smaller part of the graph that doesn't cover the whole thing. So I don't know if that's something that was actually mentioned. Yeah. So basically everything we've mentioned so far that you can find inside another graph is a subgraph. So, e.g. cycles, paths, connected components. They're all subgraphs because they're made out of edges and vertices that are inside the graph. So, nearly there. The last thing that you can find inside another graph is a spanning tree. Love a spanning tree. So it's a definition. A spanning for graph G is a subgraph T. I should give it just a second. I need to refer to the edges and to the vertices. Is a subgraph T such that T uses all the edges of G, all the vertices of G. T set of vertices is V, as it covers all the vertices, basically. And there's an awesome theorem that says that if that any connected graph has a spanning tree. Now, why would that be important? Well, it would be important because I think when you're searching down, when you're searching for things inside a graph, it's much easier to search for things inside a tree because of the way that things are connected inside a tree than it is to search for things inside a graph. Because if you're working your way along a tree, you can find the starting point for the tree, the root, and work your way forwards from there. Whereas in a graph, if you're starting at any vertex of a graph, there's a lot of choices for where to go. But in a tree, there's less choices. So from a sort of a search and computer science point of view, trees are nicer than ordinary graphs. That's my idea behind it. And then there's like a minimum spanning tree that is the spanning tree with the least weight. In a weighted graph, the minimum spanning tree has the smallest total weight. And apparently there is one, and there's this algorithm that finds it. It's called Kruskal's algorithm. Which I'm not going to describe because you can look it up. At the moment, my plan here is to just organise everything. So if I were doing this not on a document camera, I would get a great big piece of paper and draw it all on one big piece of paper. When I was in first year, I actually had a great big window in my room and I would write on it in whiteboard marker. And these days, I would take a photo of it, but of course, phones didn't do that when I was in first year. So, yeah. But at the moment, this is what I'm doing. I would also possibly write everything down on bits of paper and literally move them around and put them together in different ways so that I could make them more organised and therefore easier to remember. So what have we got? We've got different types of graphs. We've got things to find inside graphs. And what we've discovered is that some of the graphs are named based on what we can find inside them. Trees are named because we can't find cycles inside them, though they're not named that. That's not the reason we call them trees. We call them trees because they look like trees, but that's what they are, and that's the only one that's really made. And yeah, loop-free graphs are named because there's no loops inside them, and those are the things we've discovered. And then there's the last thing that we might want to do with a graph is know some numbers about it. So we want some numbers to know about a graph. So now it would totally still be maths even if there were no numbers involved, but it feels more like maths if there's numbers involved. And any time when there's something that's got a finite number of things, you can count stuff. And so we can start counting things inside our graph. And there are any number of things that we could count. So let's see what things we can count. Just at a particular vertex, we can count what's going on at that vertex. At a vertex, the out degree is the number of starting here. Well, let's call the vertex V, say. It's a little v, not a big V, by the way. I will call it A because that just is confusing. At a vertex which is called A, it's the number of edges that's starting at A, and the in degree is the number of edges ending at A. And they go for directed graphs. In an undirected graph, you just go the degree. So for undirected, the degree is the number of edges at A. But this is in the new definition of undirected where we don't draw both directions in the graph. So yeah, if you actually look at the specific definition of an undirected graph, which actually has two edges going in both directions, technically the degree would be twice as many, but that's not the way we talk about it. You just literally count how many there are. So as an example, in this directed graph, one, two, three, four, five. So the degree, the out degree of vertex number 1 is 3. The out degree of vertex number 2 is 1, because it's only got 1 coming out. The in degree of vertex number 1 is 0. The in degree of vertex number 2 is 2, and so on. You can just count how many there are pointing in and how many there are pointing out. It's okay to have 0. That was for a directed graph, but for an undirected graph, which I will also number 1, 2, 3, 4, 5. Maybe 6 as well. For an undirected graph, we can say the degree of vertex number 1 is 2 because it has 2 edges there. The degree of vertex number 2 is 4 because there's 4 edges there. The degree of vertex number 6 is 0 because there's no edges there, and so on. That's what a degree is. So that's what we do when we're looking at just a single vertex. When you look at a single vertex, you can count up how many edges there are at that vertex. For the whole graph, you can count how many vertices there are in total, and you can count how many edges there are in total. So that was at a vertex. And there isn't a name for that. Like, there is no name for the number of vertices. Sometimes they use the letter M for it, but that's just a convenient letter. Sorry, M is the number of edges. Sometimes you use the letter N for the number of vertices. It's tradition to use N, but there's nothing stopping you using whatever letter you want. For the whole graph, you can count all the vertices. Doesn't have to be N, but usually. And you can count all the edges. And this symbol means the size of that set. They don't have to be N and M. There's no particular reason you have to do that. I've seen maths books with graphs that call it V and E, which is a bit more reasonable. Yeah, you can do that. But what you can do now is that if you know what type of graph you've got, you can count how many vertices and edges it has, and you can count the degree of all the vertices and the degree of all the vertices if you know what sort of graph it is. Alternatively, you should be able to figure out the total number of edges if you know what the degree of every vertex is. So if instead of actually drawing this graph, I just told you just the list of degrees for each vertex, you couldn't necessarily draw the whole graph and be absolutely certain which vertex went to which edge connected which vertices, but you could figure out how many edges there were in total from that information. And so now we've sort of got some problem solving to say that, well, we can relate these things to each other based on the information we have about the graph. Okay, so in any graph, we know that if you add up all the degrees, you're going to get the same answer as just twice the number of edges. The sum of the degrees for all the vertices is equal to 2 times the number of edges. So in your notes it says, i.e. if the vertices are V1 up to Vn, and the number of edges is m, then the sum over all the values of I of the degree of vertex number I is 2m. So that's our first relation, and I'm going to put a box around it because it's so important. My PhD thesis, which was not about graphs but was about other things, was mostly about counting stuff like this. Okay, so one of the classic maths tricks that you use to count stuff in this way is that you sort of go, hey, what we'll do is we'll think about an object in my head which is a vertex and an edge that's connected to it. And we're going to go, well, every vertex has a certain number of edges, so we can add them all up. And every edge has 2 vertices. And so the total number of edge-vertex pairs must be 2 times the number of edges, because every edge has 2 vertices. But it must also be what you get when you add up all the edges that are connected to all the vertices. So that's the proof of how that goes. And you can see it on the proof goes like that. I don't know if I want to write it down. Okay, so in any graph we can do that. What else do we know? In some of our famous graphs that have names, we can calculate all the vertices and all the edges. So in some special graphs, the number of edges in Kn is n choose 2, which is the same as a half times n minus 1. Oops, sorry. So e.g. K5 has not equal to has a half times 5 minus 1, which is a half times 5 times 4, which is a half of 20, which is 10 edges. So that's our first special graph. The number of edges in KNM, the complete bipartite graph, would be n times m. Because remember what happened when I drew that graph? I went down on the left-hand side and I said this has to be connected to all of them, and this has to be connected to all of them, and this has to be connected to all of them. So all the ones on the n side have m edges coming from them, so that's n lots of m edges, so n times m. That's how we know how many there are. So that's some special graphs. In a tree, so if you've got a tree which has these vertices and these edges, then the number of edges is one more than the number of vertices. Pretty sure, maybe one less. Yeah. The number of edges is the number of vertices minus 1. And that's because a tree has no circuits. So, cycles. Nah. A tree has no cycles, which means that you can't come back to where you are eventually, and so it tends to have the property that vertices are connected to ones further down on the list, and so you end up with no vertex can sort of every vertex is connected to another one, and that's connected to another one further on, and so I need a better way of explaining that. I'll look at the proof in a second, but basically it's saying, well, since the edges go between two vertices, if you sort of start at the beginning and remove that one, then every edge sort of goes towards one vertex. And so without the first vertex, there's the same number of edges as vertices, and so that's why there's one less. That's how I think about it. I have to draw that picture rather than waving my hands. I could probably even do the proofs of each of these, because these are classic exam questions, aren't they? Prove these things. That's like a good plan. And then I might stop and possibly talk about something else, we'll see. But I think I've done most of the things other than do a couple of proofs, but I think it wouldn't be the worst thing to do proofs now. Have I missed anything in anyone's memory about numbers of things inside graphs? Have we been looking at that? Did we try and calculate that, or did we use like a matrix to do that? Okay, cool. Work on that in a minute, but that's where we get to matrices. Okay, so we've got these proofs. I can do this. So prove Can I just number these so that I can show you which proof is which? 1, 2, 3. All right. Proofs. Number 1. The number of edges in the complete graph with n vertices is n choose 2. Well, here we go. Consider the pairs of vertices. Every edge connects, there's an edge between every pair of vertices, so that must be the number of edges. There's an edge for each. Okay. So we'll count how many pairs of vertices there are. The first vertex, there are n choices. The second vertex, there are n minus 1 choices, because I've already chosen the first one. But since it doesn't matter what direction anything's in, so I must divide by 2. So number of edges must be n times n minus 1 divided by 2. You could also do a much more direct argument. You could say, or a pair of edges, not pair of edges, a pair of vertices is 2 vertices chosen from n vertices. The number of ways to choose 2 from n is n choose 2. I mean, that's what n choose 2 is. And you're allowed to say that because over in the other part of the course, you did all this stuff about counting. So you're allowed to just do that. Number 2. So in K, N, M, there are 2 sets of vertices, U and W, with the size of U equals N and the size of W equals M. Every vertex in U is connected by an edge to every vertex in W. So each has M vertices at it. It's a very, that's grammatically correct. Okay. So have n groups of M, not vertices, edges. Man. Each has M edges at it. So we have n groups of M edges. Thus, nm in total. Sorry about that, about the not being able to see what was going on. And the last one, I may have to look up, because I'm not sure I can do that off the top of my head without gaining a little experience first. Induction. Bang. Okay. All right. So the way I've written my proof, my statement, is that the number of edges has to be the number of vertices minus 1. So that the way I've written it sort of implies that I started with the vertices and then created the edges from there. But I could just as easily rewrite it like this. Like that. And in that case, I could start with the edges and find the vertices from there. Which is how the proof in your notes goes. So, let the number of edges be m. And we know that m is greater than or equal to 0. This is a very, very clever proof, way of going about this proof. Induction is specifically designed to prove things about natural, like whole numbers. And so I've got a graph and I know that the number of edges is a whole number, and so it's not unreasonable to expect that induction would help. And you saw me trying to describe how things are going, and my best way of trying to describe why one was more than the other was to talk about starting in a particular spot and building the tree from that point. And so when your best way of thinking about something is to build it up from a smaller thing, well, that's exactly what induction is about. Induction is about building small numbers from the numbers before it. And so that's why you would expect to use induction for this. If your lecturer asked you to prove one of these things in an exam, or just, you know, on the street because they wanted to steal money from you and said, prove that, you know, whatever, but, you know, or old mug you, they would normally be not so nasty as to just mug you, but to tell you that you ought to use induction. But if they didn't, you now know that induction is not the worst plan. Okay. So, I know that I'd start with m equals 0, that's how induction goes. And then I go, well, it doesn't have any edges, but being a tree, it's connected. And the only way to have no edges and be connected is to have exactly one vertex. I think that I said earlier that there might be such a thing as an empty graph, but I reckon that's not true. I reckon a graph has to have at least one vertex, because otherwise my proof doesn't work. So there's no edges, but a tree is connected. Might be an easier way to say that, but a tree is connected. So if it had two vertices but no edges, it wouldn't be connected. So it has one vertex. Assuming there's no such thing as an empty tree. Okay, so therefore the number of vertices, which is 1, and the number of edges is 0, and so that works. You know, and 1 equals 1, 0 plus 1. Okay. So true for m equals 0. All right, so what I'm going to do is I'm going to do my induction. So now I'm going to go, suppose for all trees with, so I suppose you could do it with m minus, with like k vertices, and then try and prove it for k plus 1. That's your traditional induction. But then there's strong induction, which says you assume it's true for every size but up to here, and then prove it for the next one. And that seems safer because I don't know how far down I'm going to have to go. I don't know if I'm going to reconstruct my tree from the next one down or from one that's like 6 down. I'm not sure. So it might be just safer to go with it, to go with the strong version. So I'm going to say, suppose it's true for all trees with up to k edges. And what I want to do is I want to show that it's true for trees with k plus 1 edges. So I reckon at this stage it might be a useful idea to give my tree a name. So we've got that, and we want it's going to be a tree with k plus 1 edges, and we want to show that it has k plus 2 vertices, because that's one more than this. Okay. So if I broke my tree, if I removed one of the vertices from my tree, no, I need to remove an edge because I need to go down to a tree that has a smaller number of edges. So if I remove one of the edges from my tree, then what I'll make is a smaller tree. And my induction says that this theorem, my induction supposal was that it works for smaller trees. So I need to make a smaller tree. But if I break my edge, it might cut my tree into 2 smaller trees. Or it might cut it into 1 smaller tree and a single point. But either way, that'll work, because I know it works for any smaller trees. So we'll do remove one edge from T to produce... Well, let's just remove one edge from T. Oh no, we'll say to produce the graph T dashed, which may or may not be a tree. Well, I suppose, actually, we do know that whatever T dashed is, it doesn't have any cycles, because it didn't have any cycles before, and all I've done is remove an edge. So I can't make cycles by removing edges. So T dash has no cycles, so it is a forest. It can't be made from any more than 2 trees because that would mean that it had to have, we would have to remove more edges than that to do that. But we don't need to know that it's made of 2 trees to do that. So basically we should say it has no cycles, so any of its connected components must be trees as well. So it is a forest. Must be 2 trees. Since we only removed one edge. Okay. So say the components of T dash are T1 and T2. Gonna kneel. With number of edges M1 and M2. and number of vertices. Well, if they have that many edges, they must have, now M1 and M2 are both strictly less than K. I like both less than or equal to K. Because we removed an edge, and these edges were these are all, the M1 and the M2 are all the edges that we had left, so in fact they add up to K. But they're both less than or equal to K, so because we assume that this works for anything less than or equal to K, their number of vertices are M1 plus 1 and M1 plus 2 plus 1, M2 plus 1, good job. They're plus 1 for both of them, so the total vertices is M1 plus M2 plus 2, but M1 plus M2, which means the total edges, total edges is M1 plus M2, therefore total edges of T must be M1 plus M2 plus 1, because we removed an edge, and so therefore number of edges equals a number of vertices equals number of edges plus 1, because this one's plus 2 and this one's plus 1. Brilliant. So the result is true by induction. I have a sneaking suspicion that they were aiming for graphs all along in this course. Graphs are really important for like search structures and all other sorts of computer sciencey things. And so in order to do this proof, we had to know how to do induction, which is why we learned induction earlier in the course. And in order to count how many edges various graphs had, we had to be able to count things, which is why we did combinatorics earlier in the course. I have a feeling that some of the things are in this course because of this is where we're headed. I do also know that induction is important because a whole lot of other things about algorithms and their complexity is all to do with induction as well. Because you have algorithms that you can have a program in computer science that refers to itself, and suddenly that's a very induction sort of thing. So that's where I feel I'm going. Right. For completeness' sake, does anyone want anything else about graphs? Oh, the matrix stuff. Right. Can't hurt. This so reminds me of doing integration over in Maths 1A. I think that revision seminar is a good 3 hours long. All right. So this is our final thing that we can do, making matrices. So from a graph, as I said right at the beginning, one of the reasons we talk about graphs the way we do is because it's easier to encode the information about them in a computer or on paper using matrices, so we might as well mention it. So you can... Oh, what's this called? It's called an adjacency matrix, isn't it? So given graph G, which is VE, with V equals size of V equals n, make an n by n matrix A with the ij entry of A equals 1 when edge like Vi, Vj is in the edges and 0 otherwise. That is the adjacency matrix. So, just so that we know what we're talking about, you can do that either with a directed graph or an undirected graph. It doesn't really matter, but the important thing about directed graphs and undirected graphs is that if you're doing a directed graph, you have to pay careful attention to where, you have to pay careful attention to which direction it's going in. Now, I is the row and j is the column, so it's sort of from on this side, from on the side and to on the top, I think. It probably doesn't really matter. Yep. So just as an example, here's my graph. 1, 2, 3, 4. I really shouldn't have done 6, but it's okay. So I need to make a 6 by 6 matrix. Like that. I'll put them all zeros, and I won't put any edges in at all. So this is a directed graph. So we're going on the left is from, and on the top is to. I'll do that in colour so that. Just so there's at least one of them. Okay, so number 1, we can go from 1 to 4. None of these things that I've written so far are actually part of the matrix. The matrix doesn't include the headings. It's just helpful to so your reader knows what you're doing. So from 1 to 4 and from 1 to 5, but it doesn't go in, 1 doesn't go anywhere else. 2 goes to 6 and it goes to 3, but it doesn't go anywhere else. 3 doesn't go anywhere. 4 goes to itself. 5 only goes to 3. And 6 only goes to 2. That is my adjacency matrix. So that was for a directed graph. For an undirected graph, I'll just do 5 this time. Something like that. So 1 is connected to 2, and it's connected to 4. 2 is connected to 1 and 5 and 4. 3 is connected to 5. 4 is connected to 2 and 1. And 5 is connected to 2 and 3. And you will notice that it's symmetric, which it should be because all the froms are also 2s. Some other things you'll notice is that my second graph didn't have any loops, which means it'll be 1, 0 all the way down the diagonal. So if there's a loop, you'll get a 0, you'll get a 1 on the diagonal whenever there's a loop. So Note, undirected graph have symmetric adjacency matrices, adjacency matrices, and loops produce a 1 on the diagonal. So one could imagine asking a person to given a matrix and say, draw the graph that goes with this, and vice versa, or given a matrix, say, is this an undirected graph? And you go, not symmetric, no. So that's that information. And then there's this really, really awesomely cool thing that you can do with it, was if you multiply the adjacency matrix by itself, it tells you how far apart everything is in 2 steps or 3 steps or 4 steps or whatever. But they're not paths, they're walks. Yeah. Sorry? So, yeah. Because you're allowed to repeat things. I'm just going to see if I can find that reference just to make sure. Where does it talk about that? At the end, after we've done matrix multiplication? Surely it's in here somewhere. I'm just going to say it. If A is adjacency matrix for G, then A squared is number of 2-step walks from VI to VJ, and A cubed number of 3-step etc. I don't feel like multiplying those matrices out. But I could, if I wanted to, just figure out a smaller piece of it if I wanted to track it. Or I could actually ask you, for example, for the graph above, for the undirected graph, what is the 2, 6, no, there isn't a 6, 2, 3 entry of A cubed? I could ask that, and then I could go back to my graph, which was this. 1, 2, 3. And I could go, well, how many 3-step paths are there from 2 to 3? So we've got 1. That's not going to work, is it? And the only way to get from 2 to 3 is to go via 5, by the look of my graph. 1, 2. There are none. There's no 3-step paths from 2 to 3. You can't get from 2 to 3. If you go 1 step, it's going to take more than 2 steps to get to 3 from there. So, no 3-step paths from 2 to 3. So the 2, 3 entry of A cubed is 0. Awesome. That would so be an awesome exam question. Yep, not paths. There are no 2-step walks. Thank you. Walks from 2 to 3. Yay! All right, but the 2, 3 entry of A squared would be 1 because there's exactly one 2-step path from 2 to 3. And the 4-step paths we could do because we could go 1, 2, 3, 4. 1, 2, 3, 4, there'd be 2 of those. And so we could figure out, or we could go 1, 2, 3, no, that wouldn't work. Yeah, 1, 2, 3, 4, 1, 2, 3, there's heaps of those. So it suddenly starts being huge when we get to A4. Yeah. So you could count yourself, but you have to be very systematic to be able to count that, which is one of the reasons why they have this adjacency matrix trick, is that you don't have to do any of the counting yourself, the matrix does it all for you. But in an exam, our ability to multiply large matrices is reduced. So, because if we had a computer, we could just say, go! All right. I guess the moral of this tale is, you know, don't on the day before, don't agree to do a revision seminar on graphs the day before. Maybe not. Also, I guess what I like about graphs is it has enough stuff to organise. And what I've noticed by going through the whole thing is that almost everything in this is actually about terminology. Like there's hardly any actual facts other than this is what this word means. And so that makes me feel less bad about it. And I do have a couple of strategies for maybe proving things. The only thing I haven't sort of covered is some of the algorithms that they've mentioned for finding things, which you might have to look up yourself. But yes, so far it's just all terminology. And well, I've learned French before, and if I can do that, I can learn graphs. And there are many fewer words in graph theory than there are that aren't English than there are in French. There you go. That's the moral of that tale. Thank you for sticking around. I hope it was helpful.